So good morning, everyone. Thank you for coming. We start this morning session with Corey Jones from North Carolina State University. He's originally from North Carolina.
Very rare, yes.
He has a PhD in mathematics from Vanderbilt University, postdocs in Australia, National University, Ohio State University, and also professor in North Carolina State University. And he will tell us, you see, in this slide, I had it here. But it was about a holographic principle for local topological order, and he will deliver a whiteboard talk.
Okay, so I'd like to thank Bernardo and Rafael for inviting me, but also just for organizing this event. This is a very cool event. If the board talk didn't give it away by now, I'm a mathematician, so explicitly not a physicist. So it's been really great interacting with physicists and especially experimental physicists who I don't usually get a chance to interact with. It's been really cool, seeing how different communities can think about the same thing and totally different. So it's really fun. Maybe I'll get to what I said in my title and abstract, maybe not. One of the advantages of doing a board talk is you can completely change what you want to do at the last second. So what I want to tell you about is topological order, and particularly I want to give you a mathematician's perspective on what this means. How's that? Is this marker sufficient for you all to see? So topological order from a mathematician's point of view. So the basic idea is you have some quantum many-body system. Maybe it's interacting electrons, maybe it's a spin system, but it has a gapped Hamiltonian. And the idea behind topological order, or one of the kind of heuristics you can use, is that the low energy effective field theory for this quantum many-body system is described by a topological quantum field theory. So this is just TQFT for short. So what is a topological quantum field theory? Well, it's just a quantum field theory that's trivial in the sense that if you look at the correlation functions on, say, flat space, all my quantum field theories are Euclidean and not relativistic, then it's trivial. But if you put this field theory on some kind of space with non-trivial topology, non-trivial stuff happens, but it will only depend on the topology. Yes?
When you say trivial, you mean Gaussian?
No, I mean really trivial. Like on flat space-time, the correlation functions for the fields are really just like zeros.
So,
yeah. It's really trivial. But when you put it on non-trivial surfaces and say 2 + 1, you have something non-trivial, but it's still kind of trivial. It only depends on the topology. The physics examples that that people like to consider Chern-Simons theories, right? This is kind of the paradigmatic example from a physics point of view. But one of the things that's really attractive about these to mathematicians is that unlike a real quantum field theory, which has all kinds of trouble, from a mathematician's point of view, making it rigorous, like defining path integrals and things like that, topological quantum field theories have a completely rigorous, mathematically satisfying definition. Originally, the first version of a TQFT was written down, the definition was written down by Atiyah in the 80s. And to a first level approximation, mathematically, what is an n+1d TQFT? It's going to assign a space, a vector space of states. So to an n manifold, you get some vector space, or Hilbert space, if we're doing real physics. And you should think of this as the space of states assigned to that manifold. And then if I have a cobordism between two things, whatever that means, just think of it as some kind of generalization of a nice map between these things. This should get sent to a linear transformation, an operator between the spaces. And these should all kind of satisfy some axioms and some compatibility. But the idea is that in this context, the vector space that gets assigned to a manifold of n dimensions, you put your n-dimensional many-body system on there, and you look at the ground state space. And that is some vector space, and it will be non-degenerate. So sometimes you hear people say non-degeneracy of ground state space as a signature of topological order, because you look at the ground state space when you can if you can manage to put your system on a surface or something with non-trivial topology, then that's where you see kind of the vector space coming from this. This part is much harder to see in a rigorous way from the physics point of view, but we kind of assume it's there when we do things. And so that's kind of the first order approximation, the story here. But what mathematicians realized at some point is that topological quantum field theories have a completely non-topological description in terms of algebraic objects. Yes, go ahead.
From the physicist part.
Okay, good. I may or may not be able to give you a sensible answer. Yeah.
I mean, the physicists would say the topological order is related to some kind of a topological degeneracy on like some manifold, like a torus, and as you increase the genus, the number of holes, the degeneracy grows in some specified way.
Exactly.
So that's the same sort of thing you're talking about.
It's exactly what I'm talking about, but a mathematician's TQFT will have a bit more structure than just vector spaces assigned to the manifolds. There's also this fancy thing called a cobordism, which you can think of it as so technically what it is the manifold of one dimension higher whose boundary components are the source and target. But you can think of this as like, if you take like a element of the torus that like does a twist, if you take the map, like you can just think of it as something like that. Like operations you can do on the manifold should give you linear operations on the ground state space. So it's a little bit more structured than just the space. There's also some kind of topological symmetry should be playing nice, should be represented on the spaces that you have seen. Yeah.
Can you give example for like famous quantum anybody and what would be the effect, like the AKLT model, like?
Yeah. So the places in physics literature where this appears are fractional quantum Hall, and these correspond to Chern-Simons theories, is my understanding. Though I have to tell you that this part of the story is maybe the part of topological words I understand the least. But maybe someone like Nikolai, who mentioned this in his talk, might have a better description of that. But yeah, so that's where you see these things.
But you're not thinking about trivial quantum spin systems.
No, I am thinking quantum spin systems, but AKLT will have a trivial topological order.
Right, because it has a unique ground state.
Yeah.
Yeah, TQT will be not completely trivial.
It's trivial. It has trivial topological order.
Right.
But okay, good. So this is a story, but there's a completely other story that has a.
Sorry, just one more question.
No, good. Yeah,
So
this is what I want.
What is your definition of topological order? So
if the low energy effective theory is a topological field theory, then the equivalence class of this topological quantum field theory as a mathematical object is the topological order in one to first order approximation. So the order is, often, you talk about order in a many-body system, there's some symmetry going on. Well, we're replacing the symmetry as the object with this mathematical structure. It's a topological quantum field theory. And I'll give you a better version that I like better in a second when I finish writing down the circle. Yeah. TQFTs are, so you can totally replace a topological quantum field theory is totally determined, it's totally equivalent to purely algebraic object. And this nowadays people call these things like higher categories. These are algebraic objects. Okay, they I'm not going to try to define one, but in 2+1D, the roughly speaking, three-dimensional or 2+1D topological quantum field theories that kind of are the flavor that you would expect to come from a quantum many-body system. These correspond to mathematical objects called modular tensor categories. And I will actually get to the formal definition of this maybe towards the end of the talk. But what you should think of is this is just a mathematical object that represents the structure of anyonic quasi-particle excitations. So, if I have, first of all, if I have if I have quasi-particle excitations in my system, then there's different types. They're called different topological charges, and so those are kind of and they fuse together in certain ways, and they decompose when you fuse them, and they braid around each other, as was mentioned in Nikolai's talk, and so there's an intricate mathematical structure you can write down. It's called a modular tensor category, and it's purely algebraic. And it turns out that these structures are the same thing as these structures. So you could also describe
a quick question.
Yeah.
So these modular tensor categories, they include the abelian and non-abelian?
Yeah, abelian and non-abelian are equal footing here. Yeah. We don't distinguish. And so instead of saying low energy effective theory, which to a mathematician kind of grates a little bit because you look at the definition of a low energy effective theory, and it's not really a model independent, well-defined thing that you can just do. I mean, you can try to like do renormalization group flow and like guess what it's supposed to be and figure it out. But if you just started with this, there's no such thing as the low energy effective theory that's kind of defined model independently. On the other hand, you might try to be able to extract, if I have a quantum many-body system, what's a rigorous definition of quasi-particle excitations, and get this kind of algebraic structure out of it. And so nowadays, what most people who work in this area would define a topological order as is it's this thing. It's the modular tensor category. So instead of saying the topological order is a TQFT as an object, it's this anion theory. It's the algebra. So some people describe a modular tensor category as characterizing the algebraic theory of the quasi-particle excitations. Okay, and then in other dimensions, there's generalizations of this that work in there's a version of this story for every dimension. Okay, good. So I don't know what to call this. Maybe take a quasi-particle excitation. And so this is kind of what I want to focus on, this arrow here. Okay, any questions?
So you're going to classify, I guess in the physics language, it sounds like you're going to classify the systems by their excitations.
That's what people would like to do. So let me tell you what mathematicians would want to do with this. I can't even spell it. Mathematician. That's why I'm a mathematician. I never passed my spelling class. I could do the equations or whatever. Okay, so mathematicians want one. So make this arrow rigorous. Well-defined and model independent. So this is something that's maybe less of interest to physicists, this model independence. But what I want is, okay, you have a quantum many-body system with a Hamiltonian. That's a perfectly well-defined mathematical object. You have Hilbert space, you have a Hamiltonian operator on a Hilbert space. This is a perfectly well-defined mathematical object. You should be able to hand one of these to me, and I apply my definition and get one of these out. And it shouldn't depend on the details of how the model works and that sort of stuff. In practice, when you're actually doing physics, when you do these arrows, you use very special properties of the system that you're studying, some in your toy model, to kind of tell you what this is supposed to be. But there's no kind of model independent definition of what this is supposed to be a priori, right? Because all of these kind of low energy effective theory, quasi-particle excitations are somehow, even though they're perfectly, you can see them in experiments, so the quasi-particle excitations and things like this, giving kind of a rigorous, they're emergent. So having a rigorous definition is a bit challenging. So one of the things a mathematician wants to do is to make that rigorous, yes.
How many particles do you need for much information do you need?
To describe these?
Right.
Yeah, so these are very complicated mathematical objects. So on the surface, you think, oh, I'm just describing you the list of anyons, which will be finite, of topological charges. Tell me how they fuse, tell me it's braiding, but they have to satisfy this coherence condition, so it's a solution to the famous, it's called the Pentagon equation. And these are a complicated system of polynomial equations that are very hard to solve. But you need this data, and mathematicians go off and just study these things on their own, and it's a very hard problem to classify these, to write them down, even to really write one of these things down as a mathematical object is non-trivial.
I guess my question is it really easier to go with that route versus to?
Yes.
I think it's easier to go the other way.
Yeah. So this way is definitely easier, and I'll talk about that later. Yeah. Well, in some restricted setting, but yes, it is easier to go this way. It is definitely easier from a rigorous perspective because if this is just defined on a lattice, how do I put it on a surface? Like maybe your Hamiltonian is in such a way that makes sense, but maybe your Hamiltonian is given to you in a way we don't even know how to make sense of putting it on a surface. What if it's not on a lattice? Like how do you do these sort of things? And then this part is very mysterious from the physics point of view about how you get the cobordisms active. Even though you can get the ground state space fairly easily just by taking the ground state space when you put it on a manifold, this part is pretty mysterious. So this is an alternate approach where mathematically it's easier to get from here to here from these than it is to get to here. Yeah. So make errors well-defined and model independent. So there's been some progress on this in the last 10 years. So Peter Nijkins and Yoshiko Ogata have told us if you have, in the special case of spin systems, gap spin systems, which is the case, it's much easier to work mathematically rigorously with spin systems than interacting electrons. So a lot of our progress has been made in the spin system case. They've told us how, if you have a gap spin system, you can, satisfying some technical assumptions, you can construct not necessarily a modular tensor category, but a braided tensor category, which is like modular categories are a special case. And so that's huge progress because we couldn't even do that for a long time. So that's really, really useful. However, there's a lot of drawbacks. They haven't solved the problem quite yet because, first of all, you have all these technical assumptions to make their error work. And in the models we care about, we can't even verify if those models satisfy these technical assumptions. So for a large class of models we care about, we don't even know if the theory applies. And in cases where it does apply, we don't even know if you get the right answer. Because if we have a lot of models where we kind of know what the right answer is, we know what the quasi-particle excitations are supposed to be in using our model-dependent formalisms, but we can't show that the model-independent one agrees with the thing we know it is. So there's still a bunch of technical open questions making this error work. Yes?
What kind of spin system? But if I have toric code, I can imagine it's pretty easy to make.
Yes, so toric code is the one example that you can make this thing work for. But really, it works for any gapped spin system. So that's the assumption, local Hamiltonian. That's it. And then you need technical assumptions on, so it's really technical assumptions about how the algebras commute with each other asymptotically in the ground state representation. So there's some technical stuff, but it's for gap spin systems.
Yeah, okay, so you have to at least know that your system is gapped.
You need the system is gapped, yeah. So it's
for some examples.
Yeah. So you need gap spin systems, but then there's this big technical assumption which is extremely hard to verify in any actual. Like if you hand me a system, and even if you tell me it's gapped, the technical assumptions that go into their framework are very hard to verify. And in toric code, you can do it, and beyond toric code, we can't really do it. Okay, so there's some problems with this approach, and I should mention what is this approach. You basically look at what are called super selection sectors of your state, and you can kind of make that mathematically rigorous and do some analysis and put a braided tensor category structure on the set of super selections. So there's some progress
systems
there.
are two spatial dimensions. You're restricting to that case?
Yeah, sorry.
Because there was that like AKLT example that was mentioned, which is the 1D.
Yeah. Let me just tell you what's going on in 2+1. But of great interest in 1 and 3 dimensions as well. I mean, one dimensions is kind of easier because everything's trivial. The topological orders are all trivial. But there's interesting questions about like SPTs and stuff.
Including the desired chain.
Yeah, so it's bosonic degrees of freedom for trivial. Yeah, spin systems. Okay. So you want to make the errors modified. So that's one thing that we want to do. What's another thing we want to do? We would love classification result. So we want to understand phases of gaps many-body systems. And what I mean by that is the same thing that you mean when you're talking about topological insulators. You have a gapped Hamiltonian. You're allowed to add local degrees of freedom and deform your Hamiltonian as long as you keep the gap open. And if you can connect to many-body systems with that sort of thing, then we would like to say those are in the same phase. And then you want to classify the connected components, exactly like Jacob was talking about. What are the path-connected components of this space, of all moduli space of all possible gapped Hamiltonian? And topological order is certainly an invariant. So if you have there's a map from these components to topological orders, but the question is, to what extent is that a complete classification? So if two gapped many-body systems have the same topological order, is it possible to find a path that deforms between them? And this is a conjecture that physicists make, which I think most mathematicians who think about this don't believe this at all. But this is what every physicist will tell you in their talk, is that topologically ordered phases are classified by this modular tensor category. So their topological order plus a chiral central charge. What is the chiral central charge coming from? It comes from if you kind of cut your system and make a boundary, you expect to have some kind of chiral-conformal field theory living on the boundary, or not. In the case not, then this will be 0. But if you do have a chiral-conformal field theory living there, it has a central charge, and so we'll throw that in there. If you take the modular tensor category plus central charge, there's some compatibility relations between the central charge and this modular tensor category. They're not completely independent of what they can be, but the conjecture is that this is a complete invariant for topological physics, but it's almost certainly wrong. It's just,
So I have so-called invertible states that
Yeah.
have trivial order. Is this correct?
Say that again.
P-times invertible states, they have trivial order.
So they have trivial topological order, but they have non-trivial central charge. So I mean, what happened was, physicists said, oh, the answer was, modular tensor categories, and then everyone's like, well, what about these EA invertible states? And they're like, oh, let's throw that in there. And so every time physicists discover a counterexample, they just throw the thing in there and say, maybe this is it, maybe this is it, maybe this is it. But I suspect a true classification in a rigorous sense will involve more information than just the topological order and central charge. But yeah, so invertible states always have trivial topological order, but they might have non-trivial central charges.
Well, you can measure it, and I think it contributes to the thermal response, right? Central charge. So.
Yeah, it's something you can measure in a system. It's just very difficult to define rigorously in a model-independent way.
Yeah, I'm just saying, as a physicist, I'm definitely interested in the central charge, even if it's a trivial logical order.
Yeah. I mean, these are interesting states for sure. Yeah.
And your restriction to spin systems, is that a Hilbert space issue? You're just trying to keep that small, or is there something?
Yeah, I mean, it's just working in the thermodynamic limit is much easier from a mathematically rigorous point of view for spin systems, because we have a global algebra of observables. You take these finite dimensional ones localized in a region, and you take the limit of them, and it's a nice algebra. Like in Emil's talk, it's all about having an algebra, or a lot of things can be understood by having the right algebra. In spin systems, the algebra of observables you have is much nicer than in fermions, where you have this CAR, C-star algebra. It's much more difficult to work with because you have continuous degrees of freedom instead of discrete degrees of freedom. Now, you could work on a lattice, but it doesn't really help that much.
For fermions, you still have this long correlation because the creation operators anti-commute, so you have long range. So unless you restrict to the given sector of the CAR, this long range correlation disappear, and then the two are the same spinning.
They're the same, but they're the same as algebras. But an important feature when you're doing this is there's a locality structure on the algebras. You talk about observables localized here, localized there, and of course there's a Jordan-Wigner transformation that maps between spin systems and fermions, but it's highly non-local. So all of this structure about where the topological order comes from, you define it in terms of localized observables. And that structure is much more difficult when you're working with fermions than it is when you're working with spin observables. So it is a technical assumption, and ultimately it does come down to the local finite dimensionality of the local observables. That's what makes it technically significantly easier, for sure. So we would like to classify these things, and I think when physicists say this, they're not necessarily referring to spin systems. They're just, I think many physicists just have a broader view of what this is supposed to mean. But if you were trying to make this into a conjecture, I would put spin system in there just to make sure I knew what I was talking about when I said the topological order, and I would use some framework. Okay, so that's a big question. And then third, another big question is you can say, okay, well, I know that these topological orders are invariant. I could just go off and classify these things too. So classify NTCs, and this has been a big program in mathematics. To try to classify NTCs that's motivated by this kind of connection. Because even if you say, oh, they're classified by their MTCs, now I want to enumerate the possible phases, so I need to classify these as well. So these are three kind of questions that mathematicians working in this area are interested in. Okay. Good. So what I'm going to tell you about today is particularly an alternate approach to this. Which basically the idea is for nice, and I'll tell you what this means. The rest of the talk will be kind of explaining this statement I'm about to make. So for nice spin systems, So this is the niceness is what the word local topological order is going to mean, but it's like nice cases of gap spin systems. You can make sense of a boundary algebra, which is a C-star algebra of observables that are kind of localized to a boundary that you get from a cut. It's not just a simple tensor product of algebras like you have here. It's a complicated thing, but the idea is that the entire topological order and all the stuff you would want to get that makes this arrow precise is captured by just having this C-star algebra. So in a very similar philosophy to what Emil was talking about on Monday, if you just get the right algebra, the rest of the physics just falls out of it. So like the topological order and all of this stuff, you can get it in a completely rigorous way. And compared to these approaches, you can show that it's modular. You can show that it gives you the right answer in the models where you know what the right answer is supposed to be. So somehow it's a more powerful approach in the special case where it applies. Now, when I tell you what nice spin systems are, you're going to say, okay, no physical spin system I make in the lab will ever satisfy these conditions. But this is actually, the study of these spin systems is not really motivated by condensed matter physics. It's more motivated by quantum information. So yeah, so you'll see what I'm talking about when I define this. But and let me say, and algebra captures topological order. So it's the same philosophy as Emil's talk captures topological order.
So I should say that even if these they look unphysical, you can still deform them and keep the gap open until you get to a physical. So.
That's correct. So it is believed that these nice spin systems I'm going to talk about represent all the universality classes of topological order in some nice regime of so-called non-chiral topological order. So the cases where these central charges are zero. These nice spin systems are believed to represent every universality class, but again, that's based on this conjecture. So yeah, so Emil's right. If you have one of these nice ones, you can deform it and keep the gap opened, and so you're really talking about that whole family of okay, good. So what does this nice mean? Well, let's see, what do I want to say? So local topological order. So this concept was first introduced by Matt Hastings, and the original paper I think was like and here's the idea. So we have a spin system. Let me come over here. So what does that mean? We have a local Hilbert space. So the Hilbert space I assign to a point is just going to be, c to the d, some finite dimensional Hilbert space. And then, and we have a lattice. And the details of this lattice aren't important. You can essentially have any kind of discrete metric space that you want. But I'm going to assume it's like z to the n or something, just for simplicity. But you can have hexagonal lattices. The symmetry of the lattice is completely irrelevant. Okay. Then for each little finite subset, lambda subset of L, we have the Hilbert space assigned to that region, which is just the tensor product over all the points in the region. So it's just the tensor product. It's k point to the tensor power lambda. So it just means I'm taking the tensor product of these point ones, but the tensor factors are indexed by the points inside my little finite subset. And you also have a finite dimensional C-star algebra, A sub lambda, which is just all the operators on this Hilbert space. So it's just M D of C. So those are the point operators, and you take the tensor product of that. So those are my local operators. Okay. What is a local Hamiltonian? It's informally already this way. It's a sum of these operators where HI are local. So they're localized to some little patch. Think like nearest neighbor terms or plaquette terms or something like that you're used to seeing in the Ising model. But the condition you need that makes it local is that the supremum of the diameter of the supports, support of HI is finite. So you don't really care if they're like nearest neighbor or plaquette or vertex terms or edge terms. You just need that all the terms in here are local operators and their support, the algebra that they essentially live in is globally bound. We're not assuming any translation symmetry or anything like that. But of course, the canonical examples will be things like, easy model and stuff where you have nearest neighbor interactions or something like that. So that's what I mean by a local Hamiltonian. And when you have a local Hamiltonian, you can define the local ground state space. So P lambda is the ground state space of H restricted to the little lambda region. So basically what this means is I just take all the terms that are supported in lambda, and I ignore all the terms that are happening outside of my little finite region, and I look at that Hamiltonian, and I take the ground state space of that. That's a subspace, right, of this case of lambda. So it's a subspace of my my local Hilbert space. And it's not in general, even if you have in the thermodynamic limit a unique ground state, these spaces are highly degenerate. Okay, and so now I'll get to the definitions. Well, I guess these are all the definitions. So first, we need to assume our Hamiltonians are what's called frustration-free, and there might be slightly different formulations, but this is a version of it. So frustration-free, what does it mean? It means this. So if I take, so suppose I have an inclusion of two finite regions. So I'm thinking here's my lambda, here's my delta. One. If I take the ground state space for P lambda and I just include it into the bigger Hilbert space by tensoring with all the factors I didn't already have. Sorry, not H, K. K to the tensor delta take away lambda. So basically I'm considering the subspace of H delta, which just takes P lambda and puts just the whole Hilbert space on all the tensor factors that I don't have. I should have that this contains P delta. So more informally, what this means is that we're saying that local ground states in the delta region are also local ground states for the lambda region. So that kind of the ground states are kind of spatial. The ground state spaces are spatially compatible with each other. This is a highly non-generic situation, right? In general, if you give me a local Hamiltonian, I do not expect this at all. You expect frustration. And even from a computational perspective, if you give me a local Hamiltonian, it's a very hard, I forget the exact computational class, but it's a difficult computational problem just to even determine if it's frustration-free at all. So this is kind of something special that you wouldn't expect generically in most of your physical systems. But again, it makes the mathematics much easier to do. So we're going to assume it's frustration-free. Okay. This is a kind of a common, when you're trying to do things like this is usually something you need to assume. Okay. Then local topological order happens when what? If there exists R bigger than 0. So now I'm going to restrict, I'm going to use a formalism that's using rectangles because I'm assuming I'm in some lattice like this. But it's easy to write down formulation for whatever lattice you want to. There's nothing really special about rectangles. Such that for all sufficiently large rectangles, with the size of this sufficiently large, whatever that means, there's some, you can make sense of what sufficiently large is supposed to mean. If A is an operator localized, okay, so let's say it this way. If delta is a subrectangle of lambda, so now let's switch the switch here. With the distance from the boundary of delta to lambda is greater than r. So the distance between delta, let me say the boundary of delta and the boundary of lambda is greater than or equal to r, just greater than or equal to r. Then I have the following equation. So if I do p lambda a p lambda equals some scalar times p lambda for all operators that are localized in a delta. So here, this p lambda, it's supposed to be lowercase where that's capital, is the orthogonal projection onto the subspace. Okay, A is some operator that is localized here. So what that means is that for all the sites outside of this region, I just have ones. So that's what I mean by saying this operator is localized in delta. And what this is saying is that if it's localized sufficiently far into the interior of the rectangle, when I squeeze it between the ground state projection of the bigger region, I just get a scalar. Okay, so it times the projection. So this compression property, you just get the scalar times the projection. So what this is saying is that if I look at my ground state space lambda, associated to lambda, and I try to apply a local operator, and I project back to the ground state space, I can't do anything. Basically, these ground state spaces have no local degrees of freedom. Because if I try to apply a local operator and project back, I just have only multiplied by a scalar, and of course we don't care about scalars when we're actually talking about the states themselves. So this is a formalization of the idea that there's no local degrees of freedom in the ground state spaces. Degrees of freedom in the interior, and that's an important point. Notice that we said this is only true for stuff that's localized away from the boundary. So this implies that any local degrees of freedom you do have to be kind of concentrated near the boundary. And this is exactly a version of the holographic principle. That was made famous by Gerald H'Tooft and Lenny Susskind when they were trying to understand the fact that in black holes the Hawking-Bekenstein radiation in that whole land is proportional. The entropy of the black hole is proportional to the surface area of the black hole. So they proposed maybe the degrees of freedom in the black hole live on the boundary, and there's not actually local degrees of freedom inside the black hole. This is kind of precisely a version of that, saying that there's somehow all the local degrees of freedom on these spaces have to be concentrated near the boundary. Because if you're deep in the interior and I try to apply a local operator that changes the space, I can't actually change the states in the space. Okay, yeah, you have a question?
Yeah, I guess this doesn't exist in 1D SPTs, right?
Exactly, yeah, this does not exist in 1D. There's only the trivial ones.
Yes, but what's special about 1D SPTs? Can you comment on that?
I think it's because the boundaries are so trivial. The boundaries of regions are kind of like for this sort of thing, the boundaries are too trivial to have, to say something interesting about being localized away from the boundary. This happens because the boundaries are 2 points. So I think that's what it is.
But these SPTs also have this string operator, which is a non-local.
Yeah, right. So you do have non-local degrees of freedom, and indeed, string operators give you examples of these non-local degrees of freedom. So I can obviously just apply an operator that will, move the states in p lambda around, but I can't apply local operators or operators localized in the interior to do such a thing. Yeah. So there's a huge difference between local and global degrees of freedom. Okay.
So this is not a statement about the model, but really a statement about your algebra, spin algebra.
Well, no, it's really a statement about these spaces of ground state
But
projection.
at the end, can you make sure that such a projection exists in your algebra? This lambda should be from.
Well, so it's really a family of projections, right? You have this infinite family of projections, and essentially it's an assumption. Like you're Hamiltonian if the local ground state projections satisfy this property.
Yeah, but the projection is already from the algebra, so it's a statement about the algebra. Now, one still has to prove that this set is non-void.
Well, it has to. It's really about the Hamiltonian because remember where these p lambdas came from. They were the local ground state projections of the Hamiltonian.
But the algebra doesn't afford such a projection.
Oh, yeah, so they do exist.
The statement is empty.
Yeah, no, they do exist because I'll give you a bunch of examples of these things. Yeah. So for example, Kataev's tort code satisfies this, but there's a whole family of examples that satisfy this. So I'll give you a bunch of examples.
So in other words, there are projections, and the corner algebra for that projection is just commutative algebra. That's the mistake.
The what algebra for this?
Corner algebra. So
No.
No.
Because this is only true when I put the A's that are localized in the interior. So there's more elements in this algebra, particularly operators localized near the boundary, for which this is not true. So it's only the corner, like a relative corner.
Relative.
Yeah. And actually, exactly the point of what I'm going to do about this boundary algebra is I'm going to take the full corner and use that as my algebra to consider. And so intuitively, you're thinking about, because of this property, when you take the full corner, what's surviving are things that are localized near the boundary. So that's like what we're doing here. Okay, good. Yeah. So why do people care about this? So the original reason that Bravia and Hastings introduced this, because they could show that under this, with like another mild technical assumption, that first of all, these Hamiltonians are gapped, okay, but that the gap is stable under perturbations. So if I perturb this a little bit, I'm still going to get something that's gapped, okay, and it's a technical result. And so it was kind of a nice, stability of gaps is a thing that mathematical physicists love to do. So that was one of the original motivations.
Good question. I mean, that seems kind of obvious. It seems like a gap cannot close perturbatively because there's an energy scale associated with it. So, I mean, how can you have an arbitrarily small perturbation close a finite size gap?
Yeah, exactly. That's the intuition. But like actually when you go down and try to prove it in the thermodynamic limit, everything becomes really challenging. So intuitively, physically, like obviously, that's the case. But then, having proofs of these things is somehow surprisingly difficult. So I agree with your intuition. That's exactly right. And the perturbations are quasi-local. They're not strictly local. So it's not like I'm just adding in a local operator in my Hamiltonian. I'm taking some kind of limit of local operators, the C star norm limit, and perturbing them. So quasi-local perturbations is what this is. But anyway, so that was maybe part of the original motivation. But nowadays, one of the reasons that this is such an interesting thing to consider is quantum error correction. Because if you're familiar with quantum error correction, this is literally a statement that if you think of this P lambda as a code space, this code space corrects all local errors. Any error that's localized sufficiently away from the boundary will be corrected by this code space. In other words, you could reformulate this in terms of quantum channels, and these are like the Krauss operators associated with quantum channels. But there's an equivalent condition in error correction. This is a restatement, a strong restatement that this code space will correct all local errors in a rigorous sense. It means if you had any error that was localized, described by any quantum channel, if it's localized in the interior, you can come up with a global channel that kind of undoes the error and recovers the original state in this code space. So people are very excited about this because, when you build quantum computers and things like this, you get lots of local errors. So the fact that these correct any local error, I don't have to have, usually when you do error correction, you have some special model of what the error looks like, and you correct for those specific errors. But these correct all local errors independently of the model form. So that's very exciting. And in fact, the canonical example of this thing that I'll write down in a minute is Kataev's Tor code. And this is exactly why he wrote down this model, or maybe, one of the most exciting things about this model is that it corrects error. And in fact, in IBM and Microsoft, people who are actually building quantum computers, they are using versions of this to correct errors. This is what people are actually doing, like in the lab, like building these things. But I'm more interested in these things as mathematical objects. But of course, there's a lot of people in the quantum error correction. Right? A lot of people in the quantum information community that are super interested in this. Yes.
Arrows should still satisfy the requirement that the gap is not closed.
Which arrows?
I mean, it cannot correct an arbitrarily strong arrow.
Yeah, so it can but it can correct an arbitrarily strong error that's localized sufficiently far away from the boundary. That's the condition, is that it needs to be far away from the boundary. But if you make your patch big enough, this R stays constant. It doesn't grow with the system size. So if you make your R really large, you make your square really large, the amount of errors, the proportion of errors that are localized away from the boundary is very large. So, if you want to correct more and more errors, you make this ground state space bigger and bigger and bigger. And of course, there's a trade-off there. Like that's harder and harder to do to make this implement on a larger thing. So there's some kind of trade-off. You're looking for an optimal situation where you kind of correct the most errors, but have this be not too big. Now, another solution is to put this on a torus, and then there's no boundary conditions, and then you just correct all local errors. And indeed, that's what people are Kitaev's original thing. That's why it's called the toric code, because when you put on a torus, there's no boundary conditions.
There is a boundary. Prefix can proliferate from the boundary. It can change.
Yeah, that's right. So you can have non-local errors on a torus because you've closed things off and it's periodic boundary conditions. It's much easier to have a non-local error that happens, which you can think of as like, if you think of an error as an excitation, think of it as like an anion. You can have a pair of particles pop up, go around the torus and annihilate, and that's a non-local error that will change the state space. It won't satisfy this property. So the problem with putting it on a torus is now you can have a lot of non-local errors. And of course, that's a problem here too, but somehow it's less of a problem because your boundary conditions are, you have a higher ground state degeneracy because your boundary conditions essentially index the ground state degeneracy. So that helps you with your non-local error issues. Okay, but anyway, so that's like quantum information stuff. Let me write down Kitaev's toric code for those of you who haven't seen it. Let's see. What time did I start? Okay.
10:35.
Good. Good. So so I don't even know if I'm going to get to tell you what a modular tensor category or a fusion category is, but that's fine. I just kind of wanted to explain some of these ideas anyway. So good. So what is Kitaev's toric code? So here you have a square lattice, and we're going to put the degrees of freedom instead of at the points, like I was implicitly doing over here. You put them on the edges. So put C2 at each edge. Okay, so we have the degrees of freedom are actually living on the edges. And then you have two types of terms. So you have a vertex term, which is like AV, which what you do is for each vertex V, I look at all the edges that are adjacent to that vertex, and I apply a poly X operator to each one of these things. So it's product of poly X, and these are localized at edges adjacent to V. So I'm just applying a product of poly X, and poly X is like 0, 1, 1, 0. I don't know if you guys use that, the poly X terminology. Just the 2 by 2. And then there's another type of term, a plaquette term, which is the product of poly Z's, where these are localized at edges adjacent to the plaquette. What is a plaquette? This is a face plaquette. I don't know why they used the word plaquette, but the face. So for each face, I look at all the edges around it. I apply poly Z, poly Z, poly Z, poly Z. Okay. So I have two types of local terms in my Hamiltonian, and you define the local Hamiltonian. It's the sum. There's a different normalization conventions, but I'll put the identity minus A sub V, and then also plus sum of identity minus B sub P. And I sum over all vertices and plaquettes. And this is just a normalization to make the ground state space be the actual kernel of these operators. This normalizes the ground state. The ground state energy to be zero. So this is the toric code model. And a theorem, which actually is pretty non-trivial to prove, but actually follows from work of Peter Nijkens, is that this is a local topological order. This is a local topological order. Or this, I guess you would say, this spin system exhibits local topological order or something. It is frustration free. In fact, so you can actually check that all these operators commute with each other. Not these operators, but the AVs and the BPs commute. And so that automatically applies as frustration free because they can simultaneously be diagonalized. It is gapped. Yes. Yeah, that is true.
On Z2.
On Z2, in the thermodynamic limit, yeah. Yeah, it's gapped, and it satisfies this local topological order condition. Good. So that's kind of the the starting point of examples. But there is a large family of examples that you can build so-called Levin-Win models. So let me tell you about that. And in order to tell you what a Levin-Win model is, I have to tell you what a fusion category is. And I'll give you the physicist definition. If you open a textbook on tensor categories and look at the definition of fusion category, your eyes will boggle, and you're like, what the? It's like some like abelian category satisfying law, and you look at the definition of abelian category, and it looks crazy. But there's a simple description. What you should think of this is describing like a system of quasi-particles, topological quasi-particles, but not in 2D, in 1D. So I don't have a braiding, but it's basically the algebraic structure of quasi-particles without a braiding. So you have a list of types, you can think of it as, and one of them is called like the vacuum or the unit. It's trivial. You have, for each triple of objects, a Hilbert space, a finite dimensional Hilbert space. I'll draw it this way, A, B, C, which I'll call V, A, B, C, which this is just a finite dimensional Hilbert space, but from a physical point of view, I'm thinking of it as all the fusion channels. If I fuse these two particles and I can get the outcome of C, there's maybe different channels that occurs, and this is the space of possible channels. And of course, you should have that the vacuum actually acts kind of as a unit. Like if I fuse the vacuum with A, there should be one thing here, so this space should be one-dimensional. Things like that, okay? Just that doesn't make the pictures make sense. But the real meat of what's going on here is you can think of it, if you want to, as a change of basis matrix. So if I fuse three particles, A, B, C, D, and they follow this channel, I need a way to rewrite that as a sum of things that are fused the other way. A, B, C, D. If I label these, so I'll try to write down the actual label and see if I can pull that off here. Sum over F. Let's see. F sub A, B, C, semicolon D. And now I'm going E to F. Well, I'll just say it this way. Alpha, beta to gamma, delta. Okay, I'm just making this notation up as I go. Alpha, beta, gamma, delta. But anyway, you pick a basis here. You want to rewrite that. In other words, left associate. I basically intuitively what's going on is there should just be one set of fusion channels for three particles down to one particle, and I should be able to write any such fusion channel as a linear combination of left associated fusion channels or right associated fusion channels. So you need a change of basis matrix, and this is just like the change of basis matrix between these two different bases of fusion channels. But okay, just writing something down like this is not enough. It has to satisfy a complicated equation called the pentagon equation. And this is what makes actually finding examples of these non-trivial. So let me write this down for you. This might take a minute. Let's see, and then I should have given myself more room. Okay, so I could apply my change of bases in this order, where first I'm kind of doing my change of basis to these terms, then I'm doing it to these terms, then I'm doing it to these terms. But there's another way I could have done my change of basis to get from here to here. I could have first changed the changed basis here, so I could go down to, okay, this is where I should have used here, why don't I, let me just erase this.
You can do it linearly.
I'm going to erase that. So you can go here, by this time I changed that basis first, and then you can change the basis down to here. So there's two different operators, change of basis matrices going from here to here. I want them to be the same as each other. So mathematically, we would say this diagram commutes, but this composition of matrices should equal this composition of matrices. That's the coherence condition. And you can prove that if your change of basis matrix satisfies this kind of tree rewriting coherence, any tree rewriting coherence you could write down will also be satisfied. So this is kind of like the minimal coherence condition on your change of basis matrix, and it applies any other coherence condition or any other kind of way you could get two different ways to get from one kind of associated tree to another. They'll give you the same answer. But when you try to solve these equations, okay, so this is essentially a fusion category. There's a little bit more details, like you need antiparticles and things like that, and they have to kind of satisfy some zigzaggy stuff. But this is the meat of it. When you try to find these, you write down this as a bunch of polynomial equations in those coefficients, in the matrix coefficients I wrote down. And it's a horrible, horrible system of polynomial equations. Our computers are terrible at solving these things. And so it's really hard to kind of brute force find fusion categories by hand. Fortunately, fusion categories appear from other concepts like representation theory and conformal field theory, and we can build them in other ways that don't require us to like solve this equation by hand every time we want to. But sometimes we need to solve these equations and they're very hard, okay? But this data, like having a solution to this equation that gives you this change of basis matrix, you should think of it as a precious, intricate, special thing. They're not just like lying around everywhere. You have to do a lot of work to actually get one in your hand. But to write down the fusion category, basically all you need to do is tell me your list of simple objects. You really only need to know the dimensions of these spaces, okay? Which are, this would be called the fusion rule, right? Like how many times does C appear as a sum n of A times B? But then the thing that's super precious is the solution to these equations. That's the thing that you don't see very easily when you're thinking about just how the physics works. Like measuring these fusion coefficients in a laboratory would be insane and is not possible as far as I know. But that's what you need to actually get a tensor category and not just some fusion rules. And that's one of the things that makes these arrows I was talking about, like if you're trying to build a fusion category out of something, it's one of the things that makes doing that hard. So I've got a little bit ahead of myself. So suppose you have a fusion category C, then Levin and Wen showed us how to actually build a spin system from this. So since I'm essentially out of time, I won't go into the details of how this works, but Levin-Wen models build a spin system, from this data of C. And a theorem is that, I guess this is due to Nijkins, no, I guess I'm the first one on that. Peter Nijkins, David Pennies, and Wallach, is that Levin-Wen models are locally topologically ordered, are LTOs. Okay, so all of these class of models you build from fusion categories, you can actually, if you squint your head and turn your head to the side, you can actually see this as a kind of a special case of Levin-Wen model. Toric code is actually a Levin-Wen model where the fusion category you use to build it is just vec Z2. It's just Z2 graded vector spaces. Okay. And so instead of kind of telling you about the original thing I thought I might tell you about this kind of holographic principle and stuff, which I sketched at the beginning, I'll just kind of leave it here. So these exhibit local topological order, and then using this framework of boundary algebras that I kind of hinted at the beginning, that Emil seemed to immediately understand without me having to say anything more, you can recover the local topological order associated to this, which is not actually this fusion category, but it's something called the Drimfeld center of this fusion category. And so I won't go into that because I'm out of time, but that's the basic idea. If you want to reframe the talk, forget about holographic principle, call this talk local topological order, and this is the main theorem, and then everything's perfect. And I did it right. So thank you guys. Okay, thanks. Yeah.